Hello, I'm Ben. I'm an instructor at Chicago Bright, and today we're going to go over a problem that was on the Tokyo entrance exam back in the 1950s. This math problem is very different at first from the normal SAT math problem, but when you look at it much more closely and try to understand fundamentally how we want to deal with a SAT math problem and how they work, I would actually argue that this is actually a very similar problem. What I mean by this is the SAT math section only requires knowledge from geometry and algebra 2, and as long as you understand those, you can generally answer any problem that's actually on the SAT math section. But a lot of students still have a very difficult time actually answering these questions, even though this is all the knowledge that's necessary, just due to the nature of these questions. Because what they're asking is not necessarily, do you understand concepts, but do you know how to apply the concepts? Do you understand how to find information? So we want to do something similar with this problem, where we're given some information. We want to go from point A to point B by using the information we have to create new information to finally lead us to a solution that gives us the answer to the problem. So let's first try to work through this problem and then try to relate it with how we want to deal with an SAT math problem. So we have complete the following inequalities by filling in the blank with A through D correctly. And then we have for function f of x equals log base x of 2. We have that A is equal to function of tangent 230 degrees, B is equal to function of tangent 605 degrees, C is equal to function sine of 1100 degrees, and D is equal to function cosine of 770 degrees. So as soon as we see a function in these type of problems, even on the SAT, you should immediately try to ask yourself, what is this function? What is its behavior? What's its domain and range? Is there any restrictions behind it? And by understanding these type of situations when it comes to functions, you can generally answer any problem that has to deal with functions as long as you take this type of approach. So let's first look at this function. Now, most students are actually very familiar with the logarithm function, but the issue with this problem is that normally when we talk about logarithms, we usually see the x or the domain where the 2 is. So normally we see a problem that looks more like this. Where a is just a constant, right? And usually this function, how it would end up looking like is something like this. Now, the issue with this problem is that we don't actually have this function. What we have is that the x is actually the base. So this means that this is irrelevant to our question. So we have to first ask ourselves, well, okay, looking at this function, what information do we know? Well, the first thing you can ask yourself is, what is the definition of a logarithm, and can I determine any restrictions of the domain just based off of that? Well, with logarithms, we know that the base can't be negative or 0. So because of this, we already know that this negative x-axis is not something that we should be considering. Now, for that means we're trying to mostly look at all of the positive x-axis. The next question I would ask is there any restrictions if I know that the domain is from 0, non-inclusive, to infinity? Well, let's try to rewrite this. If we rewrite this, say y is equal to log x2, we can also say that this is the same as saying x to the power of y equals 2. Now if we look at this, we probably realize another domain that's actually another x value that's within this current domain that I determined that doesn't work. And that number would be 1. The reason for this is if I put 1 to the power of anything, I can choose any power, I'll still get the value of 1. So that means at x equals 1, we actually don't have a value. Or in other words, we have an asymptote at x equals 1. Okay, so now that we have that out of the way, the next thing you should probably be considering is, okay, now what's the behavior? How does this function relate? How does this asymptote play into all of this? So let's first think about the first domain range we should consider, which is from 0 to 1. So let's think about a number that we can choose for x that easily gets us some type of y value so we can kind of check what the behavior might look like. In this case, I think an x value that works very well is 1/2. Because easily we can just say that the reciprocal, or y equals -1, gives me 2. So we already have 1 point. Let's try another point. Let's say 1/4. In this case, the y is -1/2 because we take the negative to flip it and create a reciprocal, and we need the 1/2 to take the square root of 4, which gives us 2. So now we have 2 points. Now we can keep going, and we notice, for example, 1/8 we can say is -1/3, and we can just keep going. 1/16 would be -1/4 onwards, right? But we'd already kind of notice a pattern here, which is that as we get closer to 0, we get a higher value, while as we get more further away and closer to 1, we actually get a much more negative value. Okay, so now that we have an idea of what the area between 0 and 1 looks like, how about 1 onward? So let's choose a number that's also easy between 1 and infinity. In this case, I would say 2 is an easy answer. So if 2 is x, then y has to equal 1, right? That one's simple, so we have 1. Now another one we can try is 4, which we need 1/2, since we need to get square root in order to get 2. We can keep going on this line of thinking and say 8 is 1/3, 16 is 1/4, so on and so forth, and we get something that looks more like this. Now, the question would be, well, what about between 1 and 2? What happens there? Well, let's try a number that is between 1 and 2. In this case, something like square root 2. So for square root 2, we know we have to square it in order to get the square root to 2 out of the square root to get 2. So in this case, we have something like this, and we notice that 2 is bigger than 1. So we have something that looks something like this. And if we think about it a little bit, what if I have a number that's just a little bigger than 1? Then I need a very big exponent for me to be able to get to 1. I mean, to get to 2, right? So the behavior of this is that we keep going up past it. So this is generally how this function probably looks like. And if you were to graph it, which for now we won't be touching a calculator because the assumption is that we can't use a calculator for this problem, we notice that this is the function that we'll get. Okay, so we're done with worrying about the function. We have a general idea of what it looks like and between what domains we have this type of behavior. The next problem we have to consider is the actual x values that we're checking within this problem. Now when we look at these trigonometric functions, the first thing that causes it to be confusing is due to the angle measurements. Most students, when they're taught trigonometric functions, are taught within a range of 0 to 360 degrees, or if it's in radians, 0 to 2 pi. Now, when we realize that, okay, 3 of these 4 values are outside the range of 0 and 360, so it might not be easy to approach at first. But when we think about the properties of trigonometric functions, we know it's cyclical. Every 360 degrees, these trigonometric functions get the same value. So in other words, if I can subtract some form of 360, I should still get the same value. So because A, tangent 230 degrees, is between 0 and 360 degrees, we don't need to worry about that. So we can look at B. So we have 605 degrees, which is outside 0 and 360. So my question is, how many times does 360 go into 605? Which is only once. So if we do this and subtract that 360, we get that tangent of 245 degrees. How about C? C is equal to F sine 1100 degrees. And we'll notice that 360 goes in 3 times, or 1080. So this is the same as saying function of sine 20 degrees. And then lastly, we have D. D is equal to function cosine of 770 degrees. And we can see that 360 goes into it twice. So we can say that this is the same as saying cosine of 50 degrees. Now, the other issue is, okay, can we really compare sine and cosine values? Because one thing you'll start to notice is, well, these aren't angle measurements that we're familiar with. As in, most of the time when you talk about trigonometric functions, the one you remember are ones like 0 degrees, 30 degrees, 45 degrees, 60 degrees, or even 90 degrees. But in this case, we can tell that, well, those degree measurements don't really add up, right? They're not going to be with any type of special triangles that we're actually familiar with. So instead of trying to think about it like that, we should probably find a way to generalize, try to compare what the values are without actually getting to them. So right now with sine and cosine, that's very difficult. We can't easily compare those values. So we can use a property where we can say cosine is equal to sine if we take 90 minus the current angle measurement. So this is the same as saying function of sine 90 degrees minus 50 degrees, which gives me function of sine 40 degrees. So we have something like this. So now we have some way to compare the sine values and the tangent values. But obviously there's no easy conversion between tangent and sine. So for now, let's not worry too much about that and see how this plays out just from starting with these comparisons. So an easy way to start by comparing these is maybe drawing a unit circle to see, okay, where do these values kind of lie? Okay, so in the case of sine, right, we know that with sine 20 degrees, sine 40 degrees, it's going to be in the first quadrant. So we can say sine 20 degrees looks something like this, sine 40 degrees looks something like this. Now, what is a sine value on a unit circle? On a unit circle, it's just a y value. So if we look at both these values, we easily realize that the 20 degrees is actually a smaller y value than the 40 degrees. Because of that, we can say that sine